In this video, we are going to look at the Born-Haber cycle. So for this subtopic, there are two learning outcomes. The first one is to construct the Born-Haber cycle for simple ionic solid using energy cycle diagram, and the second one is to calculate enthalpy changes using Born-Haber cycle. To construct a Born-Haber cycle using energy cycle method, so basically there are 4 steps to follow through. Step number 1 is to determine the ionic formula for the cation, anion, and also the compound. Step number 2, only you start the energy cycle by first writing the enthalpy of formations for the compound first. Then step number 3, we can complete the whole energy cycle by including enthalpy of atomization, ionization energy for the metal, and electron affinity for the non-metal, and also the lattice energy. So then only in step number 4 you calculate the unknown of the enthalpy by applying the Hess's law. So now I'm going to use potassium oxide as the example to go through all the 4 steps to construct the Born energy cycle using energy cycle method, and also to determine the enthalpy change of unknown using the Hess's law. So step 1 is to determine the ionic formula for the cation, anion, and also the compound. Our compound here is potassium oxide. So potassium oxide consists of metal and non-metal elements. So this is ionic compound. So potassium is group 1 metal. So to achieve octet electron arrangement, potassium atom need to donate 1 electron to form uni-positive charge potassium ion. So here potassium atom metal donate 1 electron to achieve octet, so means that later on it is going to involve only the first ionization energy. So how about oxygen? Oxygen is group 16 non-metal element. So to achieve octet electron arrangement, oxygen's atom need to accept 2 electrons to form oxide ion. So means that later on it is going to involve first electron affinity and also second electron affinity for oxygens to form oxide O2- ion. And then how about the ionic formula for the compound? So our compound here is potassium oxide. So the cation is potassium ion. So K plus ion, and also anion oxide ion, or 2- ion. So in order to get the ionic formula for potassium oxide, basically 1 and 2 need to cross, and you get K2O as the ionic formula for the potassium oxide compound. So if in exam you do not know that potassium metal is group 1 metal, how are you going to know what is the ionic formula for potassium? So basically you just need to read the question and look at the ionization energy. So here is only first ionization energy being given to you. So means that potassium, the metal, is only need to ionize until K plus. Then how about non-metal oxygen? So non-metal, we look at electron affinity. So can you see that the electron affinity given is first electron affinity and second electron affinity? So means that later on oxygen's atom need to first receive 1 mole of electron to become O- ion, and then O- ion need to receive another mole of electron to become O2- oxide ion. So now we move on to step number 2, start constructing the energy cycle with writing the enthalpy of formations of the compound first, and our compound here is potassium oxide. So to write the enthalpy of formation, we shall look at the definitions of enthalpy of formation first. So enthalpy of formation is defined as heat change when one mole of a compound is formed. So means that when we want to write the enthalpy of formation, we shall start writing the compound first. And the compound is formed from its element in their most stable state under static condition. So elements in their stable state refer to what are the elements inside the compound, and the elements must be in the most stable state. So for example, potassium oxide here, our compound is potassium oxide K2O solid. So what is the elements in potassium oxide? So it will be potassium metal. So potassium metal is also solid, and also oxygen. Oxygen in the most stable state is O2 gas. So this is our enthalpy of formations of potassium oxide equation. And don't forget, now we are constructing the energy cycle, so we need to put in the enthalpy change value in. So how to complete the Born-Haber cycle? So in step number 3, we must include the enthalpy of atomizations for both metal and non-metal. And then for metal, we must include the ionization energy, non-metal include the electron affinity, and complete the whole cycle with lattice energy. So after second step, we already have the enthalpy of formation for potassium oxide. So to complete the balance equation for enthalpy of formations of potassium oxide, 2 moles of potassium metal solid is needed, and half moles of oxygen gas is needed. So now we need to include enthalpy of atomization, ionization energy, and electron affinity and lattice energy. So we shall look at them step by step how to include them. So first, for potassium solid, we need to atomize it to become potassium gas using enthalpy of atomization. Still remember what is the definitions of enthalpy of atomization? It is defined as heat absorbed when 1 mole of gaseous atom is formed. So 1 mole of gaseous atom is formed, but here we are having 2 moles of potassium gaseous atom formed. So because of that, the enthalpy of atomizations of potassium, positive 90 kJ per mole, we need to multiply by 2. After we have atomized the potassium, we need to include the first ionization energy of potassium. So still remember what is first ionization energy definition? It is defined as 1 mole of electron is completely removed from 1 mole of gaseous atom to form 1 mole of unipositive ion. So however, here we are having 2 moles of potassium gaseous atom. So we need to remove 2 moles of electron to form 2 moles of unipositive charge potassium ion. So because of that, for the first ionization energy of potassium, we also need to multiply by 2. So now we move on to look at oxygens. So again, first we need to atomize it. Okay, so again, enthalpy of atomization is defined as heat absorbed when 1 mole of gaseous atom is formed. So here we form 1 mole of gaseous oxygen atom. So because of that, the enthalpy of atomizations of oxygen, we just multiply by 1. And then the gaseous oxygen atom Remember, we need to make it into O2 minus ion. Okay, so how to make it into O2 minus ion? So first, the gaseous oxygen atom need to accept 1 mole of electron to become O minus gaseous ion first. This is first electron affinity. Again, this one is multiplied by 1 because first electron affinity is defined as heat change when 1 mole of electron is received by 1 mole of gaseous atom to form 1 mole of -1 ion. So here also we are having 1 mole of oxygen gaseous atom, so receive 1 mole of electron to form 1 mole of -1 gaseous ion. So it's just multiply the first electron affinity of oxygens by 1. Okay, so -1 oxygen ion is not what we want. We want it to become O2 minus, remember, to achieve octet. So how to make it into O2 minus? So you need to undergo second electron affinity. So O minus ion need to receive another 1 mole of electron to become O2 minus ion. Okay, so this is second electron affinity. Again, 1 mole of O minus oxygen gaseous ion receive 1 mole of electron to become 1 mole of O2 minus gaseous ion. So again, involve only 1 mole. So the second electron affinity of oxygens also multiplied by 1 only. And then complete the whole Born-Haber cycle with lattice energy. So still remember what is lattice energy? So lattice energy is defined as a heat release when 1 mole of solid ionic compound is formed from its gaseous ions. So we already have the gaseous ion. What we need to do is just write the arrow to the solid ionic compound, which is K2O solid here, our potassium oxide solid, to complete the whole Born-Haber cycle. So the last step is to calculate the unknown enthalpy change by applying Hess's law. So our unknown enthalpy change here is the lattice energy. So how to calculate the lattice energy? So we need to apply Hess's law. So what is the definitions of Hess's law? Hess's law states that the total enthalpy change is the same, doesn't matter whether the reaction is taking place in one step or in a series of steps. Here, our one step is the enthalpy of formation. That's why we need to equate enthalpy of formation equals to series of steps. And our series of steps here is 2 times the enthalpy of atomizations of potassium plus 2 times the first ionization energy of potassium plus enthalpy of atomizations of oxygen plus first electron affinity of oxygens plus the second electron affinity of oxygen plus the lattice energy for potassium oxide. Then we just need to substituting all the value, rearrange the equations to determine the lattice energy for potassium oxide, which is equals to -2329 kilojoule per mole. That's it. Thank you.